All right, so this is actually my final presentation of my PhD. I actually started my PhD in 2017 and I gave this talk at Future. I was in Townsville and I've modified it a little bit, but I thought it'd be nice to round it out. So it's partly honours thesis, partly PhD thesis. And I need to acknowledge my supervisors and co-authors on the work, so Dave Cook, Seb Meffray, Mike Baker, Lejeune, Jeff Steadman, Mark Norman from ANU, and John Hoy, who is not related, although we do look the same. So, all right, so just an outline. I'll go over a very brief detail of Macquarie Arc, the geology of the North Parkes District, which John covered off early in the week pretty well, the 230 prospect geology, and evidence of multiple hydrothermal overprints, which is probably one of the more interesting things. As well as the Breccia itself, I suppose. The geochronology of the prospect, and then wrap it up with some conclusions. Probably first thing I should do is to name 230 is a little unusual, and the story behind it is that the rig geo got a phone call at 2:30 in the morning, and the driller sent him a photo and said, should we keep drilling? And the answer was yes. And I'm assuming that John Hoy wasn't in the rig geo, because I've rang him a few times and he doesn't generally answer his phone. All right, so quick overview of the Macquarie Arc. I'm pretty sure everyone knows where we are in the world. So 4 Ordovician volcanic belts separated by turbidite sequences, and economic porphyry mineralisation is mainly in the western and central belts. That's awesome. So there are porphyries in the Rockley Gulgong, and not discounting it, they are there, but just main economic ones are in the Junee, Narromine and the Molong belts, as we know, and Kiandra's kind of a sick little sister, but I'm sure someone will find something down there at some stage. And then there's numerous skarn epithermal mineral deposits, as we all know, and one of my colleagues at the University of Tasmania, Tom Sharp's put a lot of time into trying to figure out the complex geometry and contact relationships using a bunch of modelling that I don't understand. And I'm not going to go into any of those details. It's pretty sliced up. So the North Parkes District, I'm pretty sure we're all pretty familiar with it, but about 350 k's west-northwest of Sydney. Mineralisation's been known for a long time, mainly alluvials and stuff, but outcropping gold base metal skarns, and Bushman's Hill stuff and vein-hosted stuff, and there's a lot going on. And hosted in the Ordovician Goonumbla Volcanics complex. And I know there's some conjecture about North Parkes District versus Goonumbla District. I'm just going to stick to North Parkes because that's what I know. The 230 prospect itself, there's a photo there of the general area. It's flat lying-ish wheat country. At the moment, if you tried to go out there, you'd have to swim or have a very good tractor. Lots of gilgai, lots of wheat, lots of old fences, but a nice area of the world to be in. So the Goonumbla Volcanic Complex, 3 main units, the Womben Volcanics, Goonumbla Volcanics and the Lungalus. Most of the mineralisation at North Parkes is hosted in the Goonumbla Volcanics. They're pretty much a series of basaltic andesite, basaltic trachyandesite, andesite volcaniclastics, interbedded latite lavas, and some volcaniclastic breccias. There's subaqueous deposition and some rafted limestone lenses which are discontinuous, and they were targets for Rio back in the day when they were looking for open pitable resources, and I think there's some ResDef done out in the area, but they're not really big enough. Well, they weren't at the time anyway. So North Parkes proper, 5 major porphyry centres on a 6 kilometre northwest southeast trending linear. There's potentially a lot more than that. Actually, there's probably a lot more than that anyway. And there's at least 7 intrusive phases identified in the district, and that's probably overly simplified based on the mining logging sequence. They're probably missing some stuff, but it's too complex. These things are too crowded together. As John demonstrated, there's monzonites intruding monzonites, and they look the same geochemically. They're very, very similar. They're alkalic and transitional calco-alkalic porphyry systems, and there's two discrete phases of mineralisation, and that's not to say that the 2 main mineralising intrusions that John talked about earlier in the week, the K-feldspar augite, ferrite quartz monzonite porphyry and the K feldspar, ferric, quartz monzonite porphyry, which are a bit of a mouthful. It's more that there's been overprinting events elsewhere in the district as well. So this is a map from Ben Jones's thesis in '91, and he mapped the geology of E44, which is an outcropping skarn, and there's another one at E7 just around the corner. These things are magnetite skarns, originally identified as gold-based metal skarns, but the gold is mainly hosted in these retrogressed domains in a single prograde retrograde skarnoid assemblage associated at the time with a microcyanite. So more of Jones's work that I'll discuss was the fluid inclusion works. Came out and he had a fractionated oxidised alkalic fluid source, which is great if you're looking for alkalic porphyries, but not so fantastic if you're looking at skarns, and sulfur isotopes. And fluid inclusion work was used to confirm that. But it turns out that the skarns are actually a passive host for gold mineralisation, so it's a rheology contrast. The thing's busted up, and the gold is actually hosted in quartz veins. So it's quartz telluride mineralisation or low sulfidation mineralisation in these skarn lenses. And just a caveat, I don't actually work for North Parks, so I don't need a disclaimer. So just an idea of the prospect geology itself. Mineralisation is hosted in moderately dipping Goonumbla volcanics, so roughly 60 towards 120, and we're assuming or inferring that they're late Ordovician basal Goonumbla volcanic sequences, so there's imbricated volcaniclastic breccias and basaltic lavas at depth. And then there's some interesting skarn stuff going on too, and that kind of serendipitously progresses downhole, which I didn't do on purpose, but it works pretty well. So you start off with a garnet skarn, which is, I think, about 30 metres downhole, and that progresses into a massive magnetite skarn with a lot of pyrite knocking around. And as an honours student logging these things, I was terribly confused, and then I was kind of happy when talked to Dave Cook recently, and he said he was also confused, and that was, nice for once. And that progresses down into a Breccia complex, and that's quite variable. So there's a chaotic matrix-supported polemic Breccia that's made up of andesites and volcaniclastics, as well as monzonite clast. And the cement phases, I've said there's five instances of brecciation in this thing, and there's potentially more, but it all got a bit overwhelming when I was an honours student, to be honest. And there's fluorite carbonate cement as a late stage overprinting, an earlier sulfide stage, and then prior to that there's K feldspar, and you can see evidence of this sort of rebrecciation of the same breccia over and over again as you progress downhole. And down towards the contact with the causative, or what's inferred to be the causative intrusion, you start to see aplite cemented breccias and coarse euhedral K feldspar pyrite, chalcopyrite cemented breccias as well. And this is all published work, by the way. It's in AJES. If I'm not explaining it clearly, you can go and read it and see if I can explain it clearly in text. And the causative intrusion is interpreted to be the 230 porphyry, which is interesting. It's got xenoliths of an earlier monzonite in the district, and evidence for the causative intrusion, or for it being the causative intrusion, comes from juvenile clasts within the breccia itself, and similar blocky euhedral veins that emanate from it. So blocky euhedral K feldspar veins that emanate from it. So very, very schematic paragenesis. There's 5 drill holes across 2 kilometres when I did this, and there's substantially more now. So there's some solid arm waving going on my behalf to put this together. An early, around 450 K feldspar hornblende ferric quartz monzonite porphyry, and that's been intruded and partially ripped up by the 230 porphyry, which is causative to the 230 Breccia complex. And then subsequent other intrusions that have similar timings to North Parks. But the interesting thing about 230 is it's actually prior to most of the mineralisation in North Parks. It's within error, but the fact that it's generally earlier, I'll explain a bit in a bit more detail in a minute. So you can see the pre-mineralisation mafic dikes occurring as these xenoliths within the K-feldspar hornblende ferric quartz monzonite porphyry, and I'm not sure that it's very clear there, but there's a dotted outline around a xenolith of the K-feldspar hornblende ferric quartz monzonite porphyry in the 230 porphyry there as well, which took a bit of digging to get out of the logging, but I got there eventually. Another interesting thing is there's zero porphyry there at 438.8, and the zero porphyry refers to the absolute lack of grade in these things, and that's with similar timing to porphyries you see at North Parkes proper, which is about 16 kilometres to the northeast. A little bit more on the breccias, so you can see that coarse K-feldspar cement phase, and in figure B there's a truncated quartz moly pyrite vein that's juvenile classed in that breccia. So multiple phases of mineralisation going on, very, very complex brecciation and paragenesis, and the other ones are just there for interest really. But fluorite is particularly interesting. It does interesting things to the metallogenesis of porphyries. You can increase the metal carrying capacity of porphyry by having fluorite as a phenocryst phase. And it's pretty abundant at North Parkes. It's not very well recognised, but it is there. And it also decreases polymerisation. I think I got that the right way round. So you can actually make a porphyry fit into a smaller space easier. And they carry quite a lot of water. I think estimates on magmatic water content are around 10 to 12%. So these things are very, very hydrous and capable of getting into small gaps. Again, this is very schematic. The undifferentiated volcanics there in green are horribly complicated. I don't understand them. There's a lot going on. There's marked diatreme facies. When they were mapped from surface, they were mapped as simple sort of southeast dipping volcaniclastics. That's not the case. They're actually multiply deformed, but not in a metamorphic sense, more of a marked diatreme kind of fashion. Not to say that all the copper's gone to surface. It's just been very, very active in the area. And the location of that 230 fault is actually pretty well debated. John Holliday disagreed with me on that one, but that's okay. Where does it fit in the geochronological framework? So the KHB QMP and the 230 porphyry predate mineralisation at North Parkes. They're within error, which is true, but based on paragenetic sequencing and looking at the rocks around the place, it seems that those uranium lead dates stack up, and this is prior to mineralisation at North Parkes. So the emplacement of the K-feldspar hornblende ferric quartz monzonite porphyry, which is pre-mineral, has similar timing to the composite biotite quartz monzonite stock at E26, so the main porphyry there at North Parkes. I did some molybdenum dating. This is actually part of my PhD work rather than my honours work. And, Mark Norman did it. I didn't do it. I just asked him to. So from E26, E48 and E44, and they indicate similar mineralisation timing, which had me scratching my head. How can you have older porphyries and younger mineralisation? What was I missing? So I've proposed the two phases of ore formation at E44 based on that disparity. And molybdenite deposition occurred broadly similar timing to Cadia East and Cadia Hill mineralisation, and the same as North Parkes, which was kind of unusual, and I had to struggle to get my head around it. So in order to do that, I decided, being from codes, it wouldn't be a codes talk without a laser map, so I decided to do some laser maps of sulfides. Almost got that out. Another point of interest where there was two age dates from the zero porphyry, so one at 455, which is consistent with basal Goonumblas, and one at 438, and that's inferred to be the true age of crystallisation of those zero porphyry dikes. I know my office mates at Codes would be pretty happy that this is a perceptually uniform colour stretch, because they gave me a hard time when I put it in rainbow, so shout out to those guys. The 230 molybdenite, which is really interesting, it's the one on the right, has the lowest rhenium content of 280 ppm compared to the moly at E48 and E27, which is up around 1200 ppm, and that had me scratching my head again. Why is that the case? And I asked Mark Norman, and he informed me that there's lots of reasons, and one of them may be that it's not necessarily a porphyry source or it's been overprinted. So that fits with the low sulfidation timing of mineralisation in the skarn at the upper surface, which is quite handy. The other interesting finding was that rhenium distribution was concentrically zoned, so there's a chance that it's been overprinted. So the molybdenite grain in figure C and F there, you can see there's quite a difference in moly versus rhenium. So moly's in figure C and rhenium is in figure F. And in the other molybdenites, it's actually quite standard. I mean, moly's quite fibrous, so that explains some of that oscillatory zoning rather than concentric zoning that you see at E44 or the 230 prospect. So more laser maps, because why not? This is work from Jeff Stedman and others, including myself, on pyrite trace element distributions. So trying to get more support for an epithermal overprint at E44. There's an early high temperature cobalt-rich core, which according to Jeff is porphyry related, and I'm inclined to believe him the amount of pyrites he's looked at. And then a subsequent gold, arsenic and cobalt as part of a subsequent low temperature epithermal overprint. The general habit of the pyrite crystal indicates that there's been some dissolution and then recrystallization, which is consistent with having fluoride-rich fluids and and acidic fluids in the area. And a copper and moly mantle to the pyrite indicating late timing, which is inferred to be related to the main stage of mineralisation at North Parks, which is again consistent with those substantially younger moly dates. So multiple pulses of hydrothermal activity with different fluid sources are proposed, which is again consistent with these two occurrences of mineralisation in the district. Wow, I've made that really short. I didn't even get a bell. All right, cool. So in conclusion, 230 is a mineralised magmatic hydrothermal breccia complex. It's open at depth, somewhat closed off, but it's still not truly constrained as to the real extent of this thing. The emplacement of the syn mineralisation porphyries predates the North Parks porphyry systems, and post-mineralisation dikes and molybdenite at 230 are co-eval with North Parks, and there's some suggestion that maybe that zero porphyry is bringing in some of that molybdenite, and it's actually an overprint everywhere, but it remains to be resolved. And the source of the high-grade, low to intermediate sulfidation mineralisation remains unresolved, but there's a lot more drilling being done since I left North Parks and finished working on my PhD. So I'm a little bit out of the loop as to what that looks like, but I'm sure John will tell me one day. All right, thanks very much.